Last time, a blind test showed something simple. Obfuscation changes how code looks, but not what it does. And what a large language model is good at is exactly that, recognizing behavior. So here is the obvious next question. If obfuscation cannot stop AI, what about encrypting the bytecode outright? The answer up front. Encryption really does defeat an ordinary decompiler. But a runtime decryption scheme running on a stock JVM falls apart just as easily. To keep the comparison honest, we reuse the same sample program, an order pricing module, 6 classes. It discounts by customer tier, hashes the order into a risk score, and builds a SHA-256 audit digest. We package it as a jar, run it once, and record the baseline output. Every recovery attempt after this gets checked against those 3 numbers: total, digest, and matrix. Now, we run that jar through an open-source encryption tool. Because the bytecode is encrypted, the jar will not start on its own. You have to attach the agent it ships with and pass the password. Drop the encrypted jar into a decompiler, and the outline of each class is still there. Fields, constructors, method signatures, but every method body is gone, and the decompiler throws an exception and gives up. Unzip the encrypted jar, and you can see why. The classes on the original path have been replaced by shells. The method body keeps only a const null and a return. The real bytecode was encrypted and moved into the META-INF directory, and its file header is no longer the standard class magic number, CAFEBABE. So against someone who just drags a jar into a decompiler, the encryption does exactly what it promises. But the JVM cannot execute a custom encrypted format. While the program runs, that agent has to decrypt the ciphertext during class loading, reassemble it into a legal class file, and hand it to the JVM. Which means that at the instant of class loading, the complete plaintext bytecode has to exist. And it only has to exist once for an attacker to catch it. The JVM ships with a package called java.lang.instrument. It lets you intercept and inspect a class before it is loaded. That is the very mechanism the encryption tool uses to inject decrypted bytecode. And the same mechanism works in reverse. An attacker can use it to intercept the plaintext. The whole unpacking agent is about 20 lines of code. The program runs to completion as usual, and meanwhile 6 class files land on disk, each one with the standard CAFEBABE header restored. Hand those 6 class files back to the decompiler, and this time, every bit of the logic comes back. Apart from local variable names, which the compiler never kept in the first place, the algorithm, the control flow, and the method signatures are all plain to read, and the discount constants and string literals are sitting there in plaintext. This is the real difference between plain encryption and obfuscation. Once you have the decrypted bytecode, what comes out of the decompiler is very nearly a mirror of the original source. The only discrepancy comes from the decompiler itself. Its type inference truncates on complex bit operations, so it printed the constant 73,244,475 as 40,763. Put the real value back, recompile, and the output matches the baseline to the character. So what about a developer with no reverse engineering background who just hands that broken decompiler output to a large language model? We ran a strict blind test, a fresh AI session, no original source, no business context, only the 6 decompiled files. When Java-C compiles a switch on strings, it first turns the hash code and an equals check into an integer index, then jumps on that index. The decompiler mistook that intermediate index for a Boolean, which is why it emitted 2 identical case-true branches. The AI recognized the pattern and rebuilt it as clean, standard syntax. The one thing it did not touch was that mistranslated constant. Blind, it had no way to read the constant pool, so it faithfully kept what the decompiler gave it. Put the 2 experiments side by side, and the difference is stark. Obfuscation replaces every class, method, and field name with meaningless symbols and encrypts the strings. Runtime encryption keeps all of the original names, stores strings in plaintext, and leaves the control flow untouched. Obfuscation trades readability for resistance, but its ceiling is set by how well AI recognizes patterns. Runtime encryption blocks the decompiler at the static level, but it hands the complete plaintext back to the JVM at class loading. Intercept that, and what the attacker walks away with is essentially the original project source. This is not one open source project getting it wrong. It is a property of every scheme that decrypts whole classes at runtime. The first kind leaves the JRE alone and decrypts with a custom class loader or an agent. The decrypted bytes still have to be handed to the JVM, and the JVM is wide open to every agent. Attach one on the side, and the plaintext is yours. The second kind pushes decryption down inside a custom JRE. That does raise the bar, but it still assembles a complete plaintext class in process memory. And as long as that complete plaintext lives in memory, a JVM-TI hook or a memory dump will pull every class back out. Both kinds rest on the same assumption, that running a program requires a complete, standard class to exist in memory. For static analysis, encryption genuinely gives you something obfuscation cannot. It takes the decompiler away entirely. But as long as a scheme decrypts whole classes at runtime, that defense is a paper tiger. Solving it properly means abandoning the idea of decrypting everything into memory. The point is not to hide the plaintext better. It is to make sure a complete plaintext class never exists in memory at all. Nothing is decrypted wholesale at class loading. The bytecode stays encrypted the entire time it sits in memory. Only at the instant the interpreter reaches a given instruction is the corresponding byte decoded in place, and the moment it has executed, it is gone.